Pluto is a distant and baffling planet that was once a part of our nearby planetary group. However, ongoing disturbing claims by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning discovery. They proposed that this cold world may be on a potential crash course with Neptune. But how could this happen, and what might be the consequences of such a massive event? Are we witnessing a fascinating cosmic oddity, or is there more to this approaching celestial disaster? Join us as we explore the possibilities of a Pluto-Neptune crash. Pluto, a former planet now classified as a dwarf planet, remains a subject of interest and study in the vast universe. According to recent predictions by leading experts, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are raising concerns about a potential catastrophic collision between these two celestial bodies, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, Pluto has not yet completed one full revolution. But the intrigue doesn't stop there. Pluto's orbit is characterized by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination, tilted at 17 degrees to the ecliptic plane. Pluto's orbital path is notably more slanted compared to other planets. This inclination and eccentricity add layers of complexity to its orbital behavior. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's. For approximately 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, challenging assumptions about their positions in the solar system. This leads to the inevitable question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers sought to understand its unique trajectory. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out due to its steep inclination and unusual shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amidst these complexities demonstrates the intricacies of celestial mechanics. The three-body problem in space involves determining how three objects, such as Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like predicting their paths based on their initial positions and gravitational interactions. For Pluto, this problem highlights how its orbit, Neptune's orbit, and the Sun's gravity interact in a complex manner. Terms like non-synchronous libration, orbital precession, and VZK oscillation are critical to understanding this phenomenon. Non-synchronous libration. In Pluto and Neptune's case, this term means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from meeting. Orbital precession. This refers to the vertical movement of a body in its orbit. For Pluto, it ensures that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, providing an additional layer of protection against potential collisions. VZK oscillation. Named after three scientists, Vladimir, Zelik, and Kai, who studied the movements of celestial bodies, this describes how Pluto, Neptune, and the Sun interact gravitationally. This oscillation explains why Pluto's orbit near the Sun appears erratic. Despite Pluto's orbit seeming unpredictable, this oscillation maintains its stability over long periods. The VZK oscillation shows that, despite the apparent chaos in space, there are underlying patterns and rules that keep celestial systems in order. These factors ensure that Pluto's orbit remains stable, preventing it from crashing into Neptune or veering off course. This three-body problem is vital to understanding how these orbits evolve due to gravitational interactions. Studying it provides insight into Pluto, our solar system, and even distant galaxies. Numerical simulations in the late 1980s revealed that, despite these stabilizing factors, Pluto's orbit is inherently chaotic. Minor variations in initial conditions can lead to massive differences over centuries. However, these peculiarities have been found to maintain stability over extraordinarily long time scales. Further research has shown how the giant planets, Neptune, Jupiter, and Saturn, affect Pluto's orbit. Neptune has a unique relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. Moreover, Jupiter's massive gravitational influence plays a significant role in stabilizing Pluto's trajectory, with Saturn also contributing. These studies highlight how the gravitational interplay between Neptune, Jupiter, and Saturn ensures that Pluto remains on a consistent path for extended periods, potentially even for billions of years. Without these elements, the solar system would be a far more chaotic place. Bodies like Pluto could collide with others or be ejected from their orbits, triggering a chain reaction with other celestial bodies. Understanding Pluto's orbit is crucial, especially when discussing the possibility of a future collision with Neptune. It provides a clearer picture of the dynamic nature of the solar system. Pluto's case demonstrates that even seemingly unstable orbits can reach a state of equilibrium through the complex interplay of gravitational forces and orbital mechanics. This also emphasizes the importance of continuous observation and analysis of these phenomena to better understand our position in the universe. The concept of orbital chaos, which refers to the delicate dependence of an orbit's trajectory on its initial conditions, is perfectly illustrated by Pluto. Even slight changes in Pluto's position or speed can significantly alter its long-term orbit. Using computer simulations has been immensely helpful for researchers in understanding Pluto's motion. These simulations use advanced mathematics to model how Pluto and other celestial bodies, like Neptune, interact. By tweaking small details in the simulations, space scientists can see how minor changes can have a profound impact on Pluto's trajectory. In the late 1980s, these simulations revealed something fascinating about Pluto's orbit. Despite its stabilizing mechanisms, its trajectory can still be highly sensitive to small disturbances, demonstrating the inherent unpredictability of celestial dynamics over vast timescales. This chaotic nature, however, doesn't necessarily mean that Pluto is at imminent risk of colliding with Neptune. The stabilizing mechanisms, such as non-synchronous libration and orbital resonance, act as safeguards, ensuring that Pluto's orbit doesn't lead to catastrophic encounters anytime soon. Why is a Pluto-Neptune collision unlikely? The primary reason lies in. Also, Neptune is impossible. It lies in their orbital reverberation. This 2-3 reverberation guarantees that for each 2 circles Pluto finishes around the Sun, Neptune finishes 3. This exact numerical relationship keeps the 2 bodies from truly coming excessively near one another, as their positions are really secured in an anticipated example. Notwithstanding reverberation, the slanted idea of Pluto's circle further lessens the probability of a crash. When Pluto crosses Neptune's orbital way, it is commonly far above or underneath the plane where Neptune ventures. This spatial detachment, joined with the gravitational impacts of the other Goliath planets, keeps their direction stable. The job of long-term reproductions, advanced computational reenactments, has been instrumental in affirming the dependability of Pluto's circle. These recreations, which represent gravitational connections with all significant bodies in the nearby planet group, reliably show that Pluto's circle stays stable for billions of years. While its circle is turbulent on more limited timescales due to aversion to introductory circumstances, the general design is kept up with over galactic periods. Anyway, researchers remain cautious. These reenactments highlight the significance of moment varieties, sometimes as little as a negligible portion of a degree in tendency or a slight contrast in speed, which could enhance over millions of years. While an impact is far-fetched in the ebb and flow epic grandiose time periods, they account for the chance of huge changes in the far-off future. Outcomes of a speculative impact. Assuming an impact among Pluto and Neptune were to happen, the impacts would be fantastic for the 2 planets, as well as possibly for the whole planetary group. Such an occasion would deliver a gigantic measure of energy, possibly disturbing the circles of neighboring divine bodies. Flotsam and jetsam from the crash could form another space rock belt or even create an impermanent ring framework around Neptune. Anyway, the Earth would almost certainly stay unaffected, given its separation from the occasion. The genuine results would be limited to the external planetary group, modifying its elements and perhaps affecting the Kuiper belt. Last contemplations. The possibility of a Pluto-Neptune impact catches the creative mind, offering an emotional viewpoint on the intricacies of heavenly mechanics. Anyway, momentum proof suggests that such an occasion is extremely implausible because of the multifaceted transaction of gravitational powers. Orbital reverberation and settling instruments still play a role. The investigation of Pluto's circle gives valuable insights into the more extensive operations of the nearby planet group. By looking at these far-off worlds, researchers can all the more effectively comprehend the fragile equilibrium that keeps our planetary area stable. Whether as a planet or a bantam planet, Pluto continues to interest and motivate, serving as an indication of the entrancing unusualness of the universe, unconventional and unprecedented. Assuming you start with just a little qualification in where Pluto is or the way in which quick it's moving, its circle could end up looking totally changed after 2 or 3 years. Yet, regardless of this evident disarray, Pluto's circle stays stable over huge time spans like billions of years. This dependability suggests that Pluto's excursion around the Sun has a sort of request to it, despite the fact that it appears to be tumultuous at first. Foreseeing heavenly developments, particularly those including unpredictable circles like Pluto's, is a colossal test. The inborn capriciousness of these frameworks implies that drawn-out estimates are frequently loaded up with vulnerabilities. While numerical models give brilliant instruments for understanding and foreseeing the future developments of heavenly bodies, they additionally highlight the impediments of our prescient capacities. These models heavily depend on the exactness of starting circumstances, and any little blunder or twisting can prompt tremendously various results, making exact predictions an overwhelming undertaking. The tumultuous nature of planetary circles like Pluto's helps remind us of the ever-changing and dynamic nature of the universe. While we've taken critical steps in understanding space, Pluto's case helps us remember how much our insight into the universe stays limited. Getting a handle on the gravitational impacts of the monster planets on Pluto's circle gives valuable insights into the more extensive elements of the planetary group. It shows how the presence and position of every planet can fundamentally impact the security and direction of different bodies within the framework. So why are leading astrophysicists of late raising worries about a possible crash between Pluto and Neptune, despite the perplexing powers at play to prevent such an occasion? Neil deGrasse Tyson, an unmistakable astrophysicist and a huge figure in advancing cosmology, offers an extraordinary point of view on the mysteries of our nearby planet group, particularly the charming instance of Pluto. Tyson, known for his role in renaming Pluto from a planet to a bantam planet, gives wise analysis on the growing understanding of divine mechanics and the public's revenue in the regions of space. Tyson's position on Pluto's renaming depends on the constantly expanding information on our nearby planet group. He sees the renaming not as a diminishment but rather as a basic acclamation to our growing perception of the different bodies circling our Sun. Tyson's approach to divine mechanics is one of continuous learning and adaptation. He sees the intricacies of circles like Pluto's as an indication of how much there is still to find in space. The premium in these inquiries keeps the investigation of space so energizing. Regardless of Tyson's confidence, his contemplations on Pluto's possible crash with Neptune paint an alternate picture. His interests about the fate of Pluto's circle suggest that we might in any case have secrets to uncover. Will Pluto collide with Neptune, or is this simply one more snapshot of disarray in the steadily advancing universe of space? Just time and further exploration will tell. For the present, we are left with a deeper interest in how little we still know about our own planetary group. We can continue to concentrate on these heavenly peculiarities, determined to uncover a greater amount of the insider secrets that lie beyond the possibility of a Pluto-Neptune crash. This brings up one more issue about the puzzling and captivating universe in which we exist. The potential for an impact between Pluto and Neptune raises captivating issues about the dynamics of the nearby planet group. It challenges our conventional understanding of planetary stability that two heavenly bodies with such boundlessly various qualities could impact. This is both disrupting and enthralling, particularly considering the current relative stability of their circles. Given that Pluto is situated in the external compasses of the planetary group, a long way from the significant planets, and Neptune is itself a gas monster with a solid gravitational field, the ramifications of such a crash would be immense for how we comprehend gravitational communications and the development of the planetary group. To fathom the dynamics of a potential effect, one must initially consider the construction and properties of the two planets. Pluto, notwithstanding being a bantam planet, contains various components. Conversely, Neptune, a gas monster, is made for the most part out of hydrogen, helium, and other lighter components, with a deep, thick atmosphere. A crash between such disparate bodies would significantly influence their design and conduct, possibly creating an occasion apparent across immense distances. What makes this hypothetical effect especially intriguing is the impact of different planets and bodies in the nearby planet group. While Neptune's gravity plays a predominant role in keeping Pluto's circle stable, it is not the only factor at play. The presence of Jupiter, the largest planet in the planetary group, is another critical part. Jupiter's enormous mass, strong gravitational field, and gravitational force provide a balancing out impact on Pluto's circle, keeping it from wandering excessively far into Neptune's area. Additionally, Saturn's gravitational influence further complicates the dynamics of the outer planetary group, making it unlikely that a catastrophic event will occur between Pluto and Neptune. However, despite the apparent stability, continuous examination has also shown that the connection between Pluto and Neptune isn't as straightforward as a clear crash course. The gravitational reverberation between the two planets, where for each two circles Pluto finishes around the Sun, Neptune completes 3, creates a sort of enormous lock that keeps them from coming into direct contact. This reverberation is a key reason why Pluto and Neptune's circles, while meeting in an immense breadth of space, have never brought about an impact.